Okay, cool. Let's get started. So I guess today we're going to talk about implicit regularization of the noise. So, and the plan today is that because this is a pretty challenging topic, and I think the research community is still, in some sense, doing research on this. So we have some results. It's pretty complicated. So what I'm going to do is I'm going to somewhat using a relatively heuristic approach. So I'm going to try to convey the main idea without doing the actual rigorous statement. So in this lecture, I don't even think I have a formal statement to state because it's just a little bit too complicated and unnecessary, right? So if I really prove the formal version of the theorem, then it probably would take 2 lectures or 3 lectures. So that's why instead I'm trying to kind of at least convey the main intuition why the noise is useful with still with some math, because without the math you don't even see the intuition sometimes. So but the math wouldn't be always rigorous, and I would like to know where it is kind of like not rigorous, and also some part cannot be made rigorous without additional assumption, and I will clarify that as well. Some part is really just for convenience I ignore some kind of like the jargons, but they can be fixed by just doing more careful math. And some part is actually fundamental challenges, and you have to really use additional assumptions or maybe even change the problem setting to go through those steps rigorously. So, so I guess the main portion of the talk, the lecture is actually not about any particular loss function. It's about generic loss function. We're going to make some special simplification for them, but you don't even need to really think about parametrization in most of this lecture. So the setup is that we have a loss function. Let's call this function g theta, and I'm also going to use x as the variable at certain cases. So, and the stochastic gradient descent algorithm, by noise I really mean the noise in SGD. The stochastic gradient descent algorithm we're going to analyze is something like this. So theta t is equal to theta t plus 1 is equal to theta t minus some noisy gradient. So we have the full gradient plus some stochastic noise. So where the expectation of this CT is 0, so this is really a mean zero noise, but the distribution CT, in the most general case, the distribution of CT can depend on theta t, right? So the noise distribution depends on which point you are evaluating at, right? So you can see this formulation, at least so far, at a very general level, does capture, for example, stochastic gradient descent, as you usually know, like the mini batch stochastic gradient descent. Because suppose you take a mini batch gradient with a few samples, then it indeed can be written as something like the full gradient plus a stochastic variable, which has mean 0. But we are not going to analyze that particular version because then the noise, it becomes too complicated in some sense, right? So we're going to analyze much simpler noise in most of the cases, like something like a Gaussian noise. So this is so strictly speaking, this is more about noisy gradient descent than stochastic mini batch stochastic gradient descent. But they do share a lot of similarities. Okay, so and what we're trying to do is we're going to gradually build up our intuition about how does this noise affect our optimization algorithm. So we're going to start with a various, like we're going to have several levels warm up. So the first warm up is that what if you have a quadratic loss function? So quadratic loss pretty much means that you have a linear model under the hood, but here I don't even have model parameterization. I only have a loss function g theta, and say we have a quadratic loss function and we have Gaussian noise. And also we have 1D, one-dimensional functions. like theta is one-dimensional. So I guess here I'm going to use, from now on, I'm going to use x as my variable, just to make it more consistent with the optimization literature. And gx, let's just assume it's 1/2 times x squared. And this 1/2 doesn't really matter. It just makes the gradient cleaner. So, so then what's the update rule for this case, right? You are optimizing a quadratic function, basically, where the global minimum is at 0, but you are using stochastic gradient descent or gradient descent with noise. So xt plus 1 is equals to xt minus eta gradient g of xt plus some noise. Let's say the noise has some scale sigma, and multiplies cct, and cct doesn't have a scale, so it means 0 on standard deviation 1. So basically, the noise has standard deviation sigma and Gaussian distribution. And now let's compute the gradient. The gradient is really just the xt, right? The gradient of 1/2 times x squared is the x, so plus sigma times cct. So this is 1/eta xt minus eta times sigma times cct. I think this one is not working. Maybe it doesn't matter. So, so what's happening here is really that this is a contraction, meaning that if you have xt, then it contracts a minimum, or make the xt smaller by a factor of 1 minus eta. And this is a stochastic term that may make xt bigger or smaller, depending on whether you are lucky or not, right? So in some sense, what happens is that, so the interesting thing is that if so when xt is large, the contraction is dominating. The contraction or the shrinking is dominating, right? Because, for example, suppose your xt is here, then what happens is that you first contract it to somewhere here, right? By multiplying 1 minus eta, and then you add some stochastic noise. So then maybe at the end of the day, you may end up at somewhere near the shrinked points, right? So, but still, largely speaking, you are moving towards 0 because of the contraction or the shrinking, right? Just because the shrinking is doing the most of the work. However, so let me finish. So the contraction dominates. However, when xt is small, or maybe xt is very small, or maybe xt is 0 for simplicity, then the noise is dominating the process. I guess this. Suppose you start somewhere very, very close to 0, then when you shrink it, it doesn't really change much, right? Because 1 minus eta times a small number is still a small number. And then you add the noise, and the noise probably make it somewhere either on the left-hand side or on the right-hand side. So the noise becomes the dominating part when xt is small. So, and eventually, basically, you are gonna converge to this second case to some extent. So because if xt is large, then you are moving towards 0, and what happens is that eventually xt becomes somewhat small, and noise is kind of like governing all the process. So eventually you are just bouncing. You are bouncing just around global mean on a certain level, right? So you cannot bounce around on some very, very high level values, because then your contraction is too large, so you wouldn't be able to bounce around that level very much. So eventually you will be bouncing around on a certain level depending on the noise level, right? So it's kind of like what happens if you have, I guess, if you think about, you drop a ball, kind of a concave kind of thing without any friction. It's not exactly the same, because there you don't have really additive noise, but you still see this bouncing around eventually, just because you can overshoot a little bit. Yeah, maybe that's not exactly the right analogy, but anyway, so eventually you'll bounce around the valley on a certain level. And how do we kind of precise it? By the way, this sounds like nothing really to do with implicit regularization, because eventually whatever you do, you always stay close to the global minimum, because there's no two global minima, right? But the intuition is very useful for future things when you kind of move away from this. So this is indeed important. So, and let's try to be more precise. And this is actually a case that we can be precise. So we can solve the recurrence. So when you solve the recurrence, what happens is xt is equal to 1 minus eta xt, x plus 1 is equal to 1 minus eta xt minus eta sigma cos ct. And then you plug in the definition of xt again, get 1 minus eta, 1 minus eta, t minus 1 minus eta sigma cos ct minus 1 minus eta sigma cos ct. And if you rearrange this, you get 1 minus eta square xt minus 1 minus 1 minus eta sigma ct minus 1 minus eta sigma ct. And if you do this for another level, you get 1 minus eta cube xt minus 2 minus 1 minus eta square eta sigma cos ct minus 2 . And if you do this, more and more, eventually what you're going to get is that 1 minus eta to the power of t plus 1 times x0 minus eta sigma times the summation. Summation looks like this. It's a linear combination of cos ck, but the coefficient in front of it is some power of 1 minus eta. So from this, you can see that, so actually there are several interesting things about this formula, which can give you some intuition. So one thing is that this thing is a very strong contraction, right? So this is the contraction part, right? And in some sense, this term comes from you contract the initial value by a lot of 1 minus eta, so that basically this becomes negligible. This becomes negligible when eta times t is much bigger than 1, because 1 minus eta to the power t is something like e to the minus eta t, and when eta times t is much bigger than 1, then and this term becomes super small. So, and you can also see from the other term, this is in some sense, you can view this as accumulation of the noise. The noise are not just adding up. The noise are accumulated in a certain way. And maybe it's easier even to look at this. So the noise that you added at last step is scaled by eta times sigma. So, but the noise that you added at the second but last one step is scaled by 1 minus eta. You have additional factor 1 minus eta. And how does this 1 minus eta come from? This is come from the contraction of the second last step. So basically, cos ct minus 1 is what you added in the second last step. And then because you do another gradient descent step on top of that, you still contract that noise a little bit, right? So or maybe you can see this from here as well, right? So this is what you got from here, but this 1 minus eta comes from the contraction in the very last step. And the same thing happens, right? So this comes from the contraction in the last two steps. So basically, every time you add noise in some intermediate step, eventually this noise will die eventually at some point if you run for long enough time, just because there's always a contraction that is applied after this noisy step, right? So that's why it multiplied in front of the noise is a geometric series, and it depends on when you added this noise, the coefficient in front of the noise, can become smaller and smaller, right? So you forget about the very long history, right? So if you add a noise at the very first step, it doesn't really matter because you multiply that. So when k is equals to, for example, t minus 1, right? That's the noise per C1 that you added in the very first step. And that noise becomes measureless because you multiply 1 minus eta to the power k in front of it. Because of the contraction, that noise becomes less and less important. So that's one thing, right? So the accumulation, of the noise is kind of like prefers the closed history and ignore the long-term history. So, and another thing is that this is a sum of Gaussian, right? Because each of these term is a Gaussian, and our assumption cos C is a Gaussian, and cos C times something is still Gaussian. And you can also compute the variance of this. So the variance of this is equals to eta square, sigma square, times the variance of each of the term, which is something like 1 minus eta to the power 2k. So, and the point is that if you take t to go to infinity, then you can know what's the limiting variance, what's the variance at the end. So if t goes to infinity, you can compute the variance of xt is roughly something like eta square sigma square. If you place t to be infinity, 1 over 2 eta 2k, and this is eta square sigma square 1 minus 1. Okay, sorry, my writing is not very clean. 1 minus eta square is how you compute the geometric series, and this is eta square over sigma square 2 eta minus eta square, but this term can be dropped because that's kind of high order term. So this is approximately just on the order of eta sigma square. Okay, so in other words, the xt eventually, as t goes to infinity, eventually has this Gaussian distribution with mean 0 and the variance something on the order of eta sigma square. So I think so here so far again we haven't really talked about like implicit bias yet, but I think we still already got some intuition about what's happening here with the convex case. So small learning rate, small eta, means that your iterate will have small bouncing around, right? So small stochasticity of the final iterate in the iterate, because your variance in the iterate xt is smaller, and you have small noise, the same thing. Also, it implies the same thing, and so basically what happens here is that the noise only makes it harder to converge to a global mean. So in some sense, if you only care about the quality of the final solution you converge to, the noise is always hurting you. Especially if you're willing to take t to infinity, right? Just because, so here you can see that when t goes to infinity, you still never converge to exactly the global mean, right? So you always have some variance around the global mean. So, and you want the variance to be as small as possible because you want to be as close to the global mean as possible. So, and the noise is only a hurdle instead of helping anything. So this is why in the classical convex case, so this is why in the classical convex case, convex opposition, typically when you think about noise, it's only about two things. It's only about A, the noisy gradient descent, leads to less accurate solutions. So this is a bad thing. That's what we discussed. And second, noisy gradient descent is faster to compute. This is because, why the noise comes into play. This is because maybe you only sample a few examples to do the sampling, right? You do an empirical, you do a mini batch gradient descent. So noisy gradient descent is faster to compute. And the only thing is that you are trading off these two factors above. That's the kind of I would say the typical way of thinking about stochastic gradient descent when you really think about a convex case, right? So noise is bad because it hurts your final accuracy, but you want to allow some noise in certain cases because you can compute faster, right? So if you think you can trade off this in the right way, you can get the fastest algorithm eventually. And you can kind of imagine how you trade off this, right? So at the beginning of the optimization, you don't care that much about accuracy. You don't care that much about converging to exactly the global mean. You want to go to the global mean as fast as possible. So that's why at the beginning, you don't care that much about noise. So that's why in the beginning, you use the large rate. And then when you're already close, right, your goal changes, right? Because now your goal is to really literally go to the global mean period. So then you cannot allow any noise. So that's why you have to decay your learning rate. So that's why there's always this kind of decay learning rate of algorithms. So so far this is about yeah. And also another thing is that just a side remark, which is useful for us, which is some useful comparison for us later. So for any fixed, suppose you fix eta and sigma, right? So the expectation of xt is always going to zero, converging to zero as t goes to infinity, right? So even though there's a stochasticity, there's a bouncing around, your average is always at zero. So this is saying that there's no bias introduced by the stochasticity. You only introduced, in some sense, some fluctuation. Of course, fluctuation is also bad, but at least you didn't introduce any bias, or systematic bias against any other directions. So, so that's another study remark, which we'll kind of like compare with in a bit. And also another small remark is that this is also called this process. Actually has a name. It's called Ornstein Uhlenbeck process. If you are familiar with this process in some other context, you can see this is actually doing the same thing. And we're going to call it OU process just for simplicity. This is going to be a kind of a basic building block for us to analyze SGD in more complex case. Okay, so we have kind of like understood the quadratic, and now let's do the multi-dimensional quadratic, which is not really much different, but I think I needed in some sense just for the sake of like future, like the future steps. So suppose you have a multi-dimensional quadratic. Suppose you have something like gx is equals to a half times x transpose ax, where A is a matrix in dimension d by d, x is the variable in dimension d, and A is PSD. So, and let's suppose your noise, because CT, now let's not assume it's just a spherical Gaussian, let's assume it has a covariance, sigma. And then your update rule, let's say, suppose we care about this process where you do gradient descent with this stochasticity CT, and then this becomes xt minus eta. The gradient will just be A times xt. You add CT, and this rearranging, you get I minus eta A times xt minus eta CT. So, and you can do the same recursion as we did before, right? We replace xt, the definition of xt, as a function of xt minus 1, and you do this recursively. Eventually, if you roll out, you get I minus eta A to the power t plus 1 times x0 minus eta times I minus eta A to the power k times c t minus k. And you can see this is still the same kind of like intuition. This is the contraction. Of course, this is a matrix. You are multiplying something less than one, less than identity. So you are contracting in a matrix sense. And here, this is how the noise accumulates, and also the noise in the history, in the very far history, supposed to take, for example, k to be close to t, right? So then c t minus k, this is something in a very, very far history. Like in a remote history. In a remote history, the noise becomes less important because there's a contraction term applied after the noise is added. So, and this is right. So, and you can, in some sense, so this becomes a more complicated formula, but you can still somewhat do the same thing. Suppose, suppose if you so you can still do the similar calculation. If A and sigma are simultaneously diagonalizable. So if they are not simultaneously diagonalizable, you can still do something to solve this, to compute this sum, to simplify this sum, but it's going to be even more complicated. So let's only think about the case when A and sigma are simultaneously diagonalizable. Then in some sense, you can just view this as, viewed as the separate OU process in the eigenspace. OU process just means one-dimensional problem in the eigen coordinate system. Because when you use the eigen coordinate system, then A and sigma are just both diagonal matrices, and then you are basically just updating in as if you are in one-dimensional case. And in some sense, for more formally, what happens is that suppose you take suppose A is U transpose, where D is this diagonal matrix, which has the eigenvalue of A, and so suppose sigma is U diag sigma I U transpose, then what you can do is that as t goes to infinity, the xt roughly comes from this Gaussian, which means 0 because this part got contracted, and you can look at the variance, which looks like something like this. The power k times sigma times 1 minus eta A to the power k. This is just because you compute the variance of the, right, so like the expectation, some matrix W c times c W transpose the covariance of this linear transformation of Gaussian is equals to W c transpose W transpose, which is equals to W times sigma W transpose, right? That's how you compute the covariance of each of these terms, and then you take the sum of them. And A is a symmetric matrix, so A and A transpose are the same. So, and you can do this, and then you can simplify this when you have the eigen decomposition. So if you have the eigen decomposition, then I minus eta A is U times diagonal 1 minus eta di, U transpose, and sigma is U diag sigma U transpose, and then you can compute this. So you can compute this sum to be something like eta squared times, I guess maybe let's also do let me just do this. Look at the k's power, you just multiply the k in front, because the U and U transpose will got cancelled, right, if you have the sequence of this. So then this becomes eta squared times sum of U diagonal, I guess I should assume this is sigma. Let's assume this is sigma squared just to make it. Let's say looking sigma squared times 1 minus eta di to the power 2k U transpose. Right, that's this matrix, and then this is the beauty of eigendecomposition, because everything becomes on the diagonal, and you have U squared eta squared U times, then this becomes, you take the sum to infinity, because I from 1 to infinity, wait, this is k. The I is for the coordinate, the k is for the sum over k, sigma I squared 1 minus eta di 2k U transpose, and this becomes eta squared times U times something like sigma I squared over di U transpose. And there's over eta here, so let's remove the eta here, something like this. So you can see that basically you have some noise, and noise is something on this level. So this is the noise level in the ith eigenvector direction. And noise level depends on this is the level. Maybe let's just be precise. This is the iterate noise, right? Iterate stochasticity, fluctuation level. Because we are computing what's the fluctuation of the iterate, and the fluctuation level in the eigenvector direction depends on the noise level in that direction, and also depends on how strong the contraction is. If the contraction is big, then you are gonna have smaller noise, smaller iterate stochasticity, because you have so strong contraction, and which doesn't allow the noise to build up. And if the noise is big, of course, eventually you're gonna have like a larger fluctuation in the iterate. Right. So, and another thing that is useful to realize is that another small remark that is useful is that this matrix U di sigma I squared di U transpose, this is always in the span of sigma, right? So if sigma has some direction where, suppose sigma is low rank, capital sigma is low rank, so in some direction there's no noise, and in those directions the xt doesn't have any fluctuation either. So that will be something useful for us in the future. And another thing is that xt, if you think about what's the rough size of xt, just look at norm of xt. This is on the order of square root eta, because this quantity is something that doesn't depend on eta, right? So if you only look at the eta dependency, then the norm of the stochasticity or the fluctuation in the iterate will be on the order of square root eta, and this is something that's probably good to remember for the moment. It will be useful for us in the future as well. Any questions so far?
So the two normal xt should be also some the diagonal.
Right. Yeah, but all of those depends on dimension. For example, it depends on how large the sigma i's and how large the di's are. But in terms of dependency on eta, this is on the order of square root eta. That's what I mean. Yeah. Yes. Sure. Yeah. I guess I'm only talking about dependence on eta so far.
That's like the standard deviation of like xt essentially.
Sure. Yep.
Or square root.
Yes.
But the size of x also takes into account like a contraction term. So is this like for large t, so the contraction term is sufficiently small? Or
yes, I'm talking about a case when t is infinity. Okay. T is going to infinity. Yeah. But okay, so maybe one way to think about this. Okay, I think I kind of sense what your question is. So this is the fluctuation in the eventual iterate, right? So in the iterate when t is kind of infinity, it's different from the noise you added at each time. So I guess actually that's actually a very good question. So if you look at the noise that you added at each time, so this is how large is this? This is on the order of eta. If you ignore, of course, you ignore other dependencies except eta. So each time you add some noise on the order of eta, and eventually all of this noise build up. They got add up together, and they add up to something on the order of square root eta. So that's how the noise kind of like accumulates, but it wouldn't accumulate to infinity, just because of the contraction, right? So because of this term that also contracts the noise to some extent a little bit, but still the noise build up with one kind of like half order higher in terms of eta, right? So it accumulates from eta to square root eta over time. So yeah. Order of eta. So okay, so we have a pretty kind of good understanding of what's happening basically. Basically, eventually, it's bouncing around with a radius, something like square root eta, in the value of this quadratic, and also you don't bounce around in those directions where you didn't add noise. Right, so that's the thing. So and now let's look at.
Is there a reasonable thing to map like the idea of noiseless directions back onto like our mini batch stochastic gradient descent idea in a natural way, or is that not enough?
So is there any way for us to map back how, like, so you want to connect back to the world where we have the mini batch gradient descent, right? So for convex case, it's not that difficult. So what you do, basically what you say is that, what is sigma? Sigma is your, so in our calculation of sigma, in our definition, a sigma is the covariance of the noise in the gradient, right? You can compute what's the covariance of the noise when you use mini-batch gradient. So you can compute that. And that is something that might change over time. But I think you can pretty much say that when you are kind of close to global minimum, the changes of the covariance of the gradient, the changes in the covariance of the gradient of the mini-batch gradient is negligible. It's even higher order term. You can basically ignore it. So basically, if you want to map this back to the mini-batch gradient, this sigma will just map to the covariance of the mini-batch gradient at the global mean theta star. So then you can get basically everything. But I don't think you get anything super interpretable anyways. So that's why I didn't get into it.
If the global minimum is very flat along some dimension, the noise will have a very large effect.
Yes, exactly. Exactly. That's exactly correct. So so suppose you have two dimension. I think this is actually a very good question. So if you have one direction which is like this, and suppose you have another direction which is like this. So the question is, how does the noise affect these two dimensions? So, and also there's a question about how do you evaluate the effect of the noise? What's the metric you are thinking about? So far I'm thinking about how does the noise change the fluctuation in the iterate, right? So suppose I'm adding noise to the same amount of noise, one unit of noise in both of these cases. I think it's indeed true that stochastic gradient descent will kind of like fluctuate more in this case. Actually, it probably wouldn't look like this. It probably look like something like maybe you do some kind of like stochastic thing like this. But this is you're gonna have a larger radius for bouncing around, and here you're gonna have a smaller radius. You're gonna be more closer to the value. However, even you have a larger radius here, it doesn't necessarily mean that you have a larger effect on a function value. because you fluctuate a lot, but the function is flat as well. So it's okay to fluctuate more in some cases. So I think let's see whether we can compute the fluctuation. So suppose you have sigma square over I di square. This is the radius of the fluctuation, and you multiply. What do you multiply? You multiply di, because di is the curvature of your function. So this is sigma I squared. This is something that doesn't depend on curvature. Di is the curvature, right? So this is kind of like x squared, right? The fluctuation you have. So if you look at the effect to the function value, it may not depend on the curvature that much, at least not for the quadratic case. Yeah. Right. So that makes sense. Okay. Cool. Okay. Cool. So, all right. So now let's talk about non-quadratic function, and then this is kind of when the things becomes interesting. But it's interesting only on top of what we have discussed. That's why we need to have the warm-up. So, so non-quadratic. And so far, I'm still doing kind of you can still think of this as a convex function, even one-dimensional convex function. So far, I'm going to change that a little bit. So, and again, for simplicity, let's say without loss of generality, let's assume the global minimizer of this gx is just the zero vector, right? So we still have a zero as the global minimizer. We are still doing something around zero. And I think I'm using the matrix notation right now here, but I think I realized that in the matrix notation, oh, I remember. Okay, so the reason why I'm using matrix notation is because then I don't have to do the two things, the scalar case and the matrix case. But for simplicity, you can, in your mind, you can pretty much interpret all of these as scalars. Okay, so I'm also assuming that because zero is the global mean, that means that the gradient at zero is zero, right? That's a necessary condition. And also that means that the Hessian at G0 is PSD. Okay, so, and let's also assume this is the part when they kind of like become not super rigorous, but we can make this part rigorous. It's just that I wouldn't have time to do all the rigorous stuff, but this part is doable. So suppose you assume the iterate are close to zero. So you start from somewhere that is close to zero, and then you can do Taylor expansion around zero. So what you do is you do xt plus 1 is equals to xt plus eta times gradient of at xt plus cct, and then you do Taylor expansion to approximate the gradient at cct at xt. So how do you do a Taylor expansion? So if you Taylor expand at 0, what you're going to get? You're going to get the nabla g0 plus nabla square g0 times xt minus 0, and plus, nabla cube g0 at xt, and maybe let's have also higher order terms, which we are going to ignore heuristically, and then we're going to get epsilon t, something like this. So I guess, if you're not familiar with the matrix thing, then I guess this is really just saying that g prime xt is roughly equals to g prime 0 times xt plus g prime 0 times xt squared plus g cubed third order derivative times, wait, what I'm doing here. So there's no xt here, there's xt times xt squared plus even higher order terms, something like this, right? So, but for matrix notation, then this, if you do the matrix thing, then this is the matrix vector product, and this is a tensor vector product. Let me explain that a little bit. So So if you do the multidimensional case, this is a third order tensor of dimension d by d by d. So, and suppose you have a t that is a third order tensor, then I'm using this t x y, where x and y are all vectors, is defined to be a vector. So this is the multiplication of this tensor with two vectors. Is first of all is a vector, and second, the definition of this is that the ith coordinate of this is the sum over jk tij xi yj. So xk y xj yk. So basically, you sum over the remaining coordinate j and k, and you leave the I alone left, and that's the outcome. So this is basically the Taylor expansion in multiple dimensions. Okay, so by the way, just a reminder for the scribe note takers, I think for this kind of small things I write on the side, you please also take notes for those, because they are useful for readers as well. If someone doesn't have time to take the lectures, they read the lecture notes. I think these small explanations are also useful. You can just have a small kind of remark of some, write it in the paragraph. That's fine. So, all right. So we have to then have Taylor expansion, and then we can see that. So we're expecting something somewhat similar to what we had done before, right? So and indeed you will see that, because this is going to be 0, because it's the gradient at 0, and this is 0. So basically what we're going to get is that xt minus eta times, okay, so I guess let me define this for simplicity h to be, as used, like h to be the Hessian at 0, then this, you can rewrite this as xt minus eta h xt minus eta cos ct, and minus the third order term. I guess I'm also going to define, let me see what's my notation here. I define t to be the third order derivative, and then this is t xt. So and higher order terms, let's ignore that from the on. Anyway, we are not going to really formally deal with them. We just have an approximation here. So, and then this is I minus eta h xt minus eta cos ct minus eta t xt. And I think you can see, I guess what I was hoping for you to see is that the third order term is something new, but the first order term and second order term are not new. The noise term and the second order term are exactly what we had before, right? So if you look at here, so for the quadratic case, you have extraction and you have a noise. The extraction is linear and you have the noise. And now the only difference is that you have additional term from the third order derivative, and that's expected, because if you don't have the third order, you ignore the third order term, it becomes just quadratic. So that's why we want to Taylor expand up to the third order, because we want to really use the fact that this is not a quadratic function. So basically, you can think of this as two processes going on, right? So one process is this OU process, kind of like basic one about quadratic, and you have additional term that kind of like make it a little bit more complicated. Right. So, and how do we proceed here? So, if you really think about So in some sense, if you, there is one thing. Okay, so this is a heuristic derivations. So in certain cases, you are kind of attempted to even drop the third order term because that may be a small term. And let's try to do that, right? So this is so just to drop the third order term, just drop it. Right, so suppose to drop it, then you have this process x is updated by something like this. Right, so this is the process. This is something we have analyzed. And we know that when convergence, xt will be something on the order of square root eta. So here, I'm ignoring all the dependencies except the dependency on eta. So, and now if you look back on what happened with this third order term, so when xt is on this order, so eta t xt, what is this? This is on order of eta squared because xt contributes square root eta. This xt contributes square root eta, and there's an eta here. So basically, you have an eta squared term, which sounds very small. Why this is very small? This is much smaller. So eta squared is much smaller than, for example, eta cosθ, right? But that probably is not unfair because cosθ is doing some random stuff. So, but eta squared is also much smaller than even just eta h xt, which is on the order of eta to the 1.5. So basically, the changes of your process, right? The two other changes of your process is these two terms, right? And this term, you can say, comparing with that is a little bit kind of like unfair because that term is doing some random stuff, right? So maybe you shouldn't compare with the absolute value of it, just because eventually there will be some cancellation. But at least you compare with the other deterministic term, eta h xt, you are still, this eta squared term is still much smaller than the deterministic term. So in some sense, it's very tempting to say that, okay, this third order term, this t xt xt thing, is very small, right? So the conclusion, would be that, so the conclusion is that this is kind of negligible. So and indeed it's true when and this is indeed true. This is negligible, and indeed it's true under one condition, when the Hessian is strictly PSD. So that's why that's when you have contraction in all different directions. So however, when H is not strictly PSD, so if, for example, in some direction, so basically, in other words, if you think about this, so this term is only on order of eta to the 1.5 when H is not 0, right? So if H is 0 in some direction, then this eta h xt term is just literally 0. So then the eta squared term is winning, right? So basically, if in some direction where H is 0, then eta h xt is just a 0 in that direction. And then eta squared becomes the largest update. Eta cosθ is always the largest if you really look at the absolute value, right? So eta cosθ is on the order of what? This is on the order of just the eta. It's always the largest, but I think I'm trying to argue that eta cosθ, if you compare with that, it's a little bit kind of like misleading in the sense that eta cosθ is doing random stuff, right? So in one step is going positive direction, the other step is going to negative direction. So eventually, so basically what happens is that if you have a random stochastic term, suppose you have a stochastic term or mean zero term, such that if you have one step is on order of eta, implies eventually, like multi-step, this will be something like on the square root eta. That's kind of like what we have discussed in the quadratic case, right? So every step, the stochastic term gives you an eta noise perturbation, and then eventually they will build up to square root eta. So, however, when you have a deterministic term, so if one step is something like eta, then eventually it's unclear what you will build up. It probably would build up to eta t because eta times little t, let's say. It won't kind of like, they won't cancel. Maybe this is a little bit, I'm not sure whether this is the best way to explain it. How do I say this? So anyway, this is a bit heuristical because, you know, it requires a little bit more. If you want to formalize all of this, it requires a little more work. But I guess what maybe let me what I'm saying is basically like the locally the largest update by like in our case, by locally the largest update of course is eta cosθ, but this one will have cancellation over time because in future you're gonna have like you can move in different directions. So that's why it's probably good to also compare with the deterministic changes, which is the eta xt. And when we compare with that, typically the deterministic changes is bigger than the eta squared term from the third order derivative. But when h is 0 in some direction, it's no longer true. So but you can so in some sense you can prove that if h is when h is strictly positive non-zero, then it's negligible, and otherwise becomes tricky, right? So if h has a completely flat direction, it becomes tricky. So I think here is a good point. Maybe let's just continue with this. So when this is case, then so in this case the third order term will introduce some biases, but very small. Some bias, but very small. And small in the sense that as eta goes to 0, this becomes negligible. And I think I have some kind of like figures here. Yes, so I have this figure. So I'm see whether you can see it. Yes. So this is a little bit small, I guess. Maybe this way. So the function is a one-dimensional function. It's a convex one. So I'm in the case where the h is strictly bigger than 0. Right? So the h, because it's one dimension, this is strictly convex function. So this is the function, but it's not like a quadratic. It's something like I think it's quadratic on both sides, but it's not the same curvature. The left-hand side is more flat, and the right-hand side is more sharp. And if you do gradient descent, so I guess probably the only thing important is this. So if you look at this is after you take 1,000 steps of stochastic gradient descent, and you can see that the mean, like the iterate, is bouncing around, right? Between this is the distribution of the iterate, distribution of the xt when t is 1024. So t 1024 is pretty big, considered to be infinity, right? So, and you can see that it's bouncing around 0. 0 is the global minimum, but the mean is no longer 0 anymore because you have the third order kind of like derivative, and the mean is something left to 0. In some sense, you prefer the left-hand side a little bit more than the right-hand side because it's easier to stay on the left-hand side. The left-hand side is flatter, so it's easier to stay there because the construction is weaker. And the right-hand side, is sharper, and you add some noise and you kind of like contract it, and you go back to 0 more quickly. So that's why the bias is towards the left-hand side where you have flatter curvature. But the bias is relatively small, you can see, right? Like you can even say this is negligible because the bias, at least, if you do take a random point, you're going to take something between minus 0.05 to 0.05 maybe, and the bias is only a very, very small number. Anyway, you are like your fluctuation is bigger than the bias for sure. So that's why in the classical kind of like in the classical kind of like optimization settings, people didn't really pay too much attention to this. I think there are some papers, I guess. So I guess there is this paper by Bach, 17, bridging the gap, I guess, between constant step size SUD and the Markov chain. So this paper characterized this effect for convex case. And you can see from the title of this paper, right, it's talking about constant step size. And why you have to talk about constant step size? Just because this will go, if you decay the step size, then this bias effect will be even smaller and it will be negligible, just completely kind of gone, right, eventually. So that's why you have to make this even somewhat useful, somewhat kind of make a difference, you have to make the step size not go to zero. So that's why in the convex case, people typically don't care about this that much. In some other cases, you care about this a little bit. This figure is from one of my recent paper with some students at Stanford, I guess. And here, the reason why we care about this is because you have you have multiple machines, and for some other reasons, you have to care about this. But typically, you wouldn't really care that much about it, just because the bias is small. Okay, so now let's go back to, now let's move on to, okay, so finally, we are moving to the implicit regularization effect. So the more complex case. I'm writing too fast, it's too cursory, I guess. With stronger implicit reg. So and these are cases where both H and sigma are not full reg. So your Hessian and your noise are both somewhat not full dimensional. And this is not something to be super surprised. This is partly comes from over parametrization. Especially, I think it's easier to think about the Hessian. If you have a manifold of global minimum, then along that direction of the manifold, your Hessian will be zero. So as long as you have a lot of different global minimum, then your Hessian will be flat, will be zero in certain directions. So, and let's say suppose, so for simplicity, let me not discuss when this can happen exactly because you need some calculations and so on and so forth. But suppose, let's say H and sigma are both in some subspace, in a subspace K, and the subspace K is low dimensional, or at least not full dimensional. And if the loss is quadratic, for the moment, just let's still think about the loss is quadratic. I guess we have to compute this. We said that the iterate will have zero, something like this. Recall that this is our calculation, sigma squared di u transpose. And so a kind of the picture, I think, is that but there's no, so basically you have no noise and no contraction, nothing in the perpendicular space of K. So in some sense, I think the function look like this when you have, so suppose you have some direction of K, this is the direction of K, and this is the direction of K perp, and suppose your function is quadratic in dimension of K, something like this. I'm not sure whether you can, I think my drawing is too bad. So imagine a valley. This is I'm drawing a valley like this. But this valley is completely kind of like oblivious to the dimension of K perp. So this thing is the middle of the valley. This is really the valley. So basically, then what happens is that if you start somewhere here, everything happens in the direction of K, and nothing happens in the direction of K perp. So you're basically bouncing around in the direction of K. So basically, you maybe go here, and go about. So you do some bouncing, like something like this. But you never move in the direction of K perp. So in K perp, it's kind of like you just know nothing. You know nothing, and you don't move at all. So that's still not kind of like that's a little bit implicit bias, implicit regularization, because the implicit regularization comes from what? Comes from initialization. If you start with this point, then you're gonna stay in this in this part. But if you start here, then you're gonna bounce around here, right? And this is exactly what happens when you have an over-parameterized linear model, because when you have over-parameterized linear model, you never leave the subspace. You never leave some subspace, and in other subspace you never move. So, but this is not the most important thing, right? So about the noise, right? Because the noise doesn't really do much. It's really just that you cannot leave a certain subspace. However, when your loss is quadratic, when your loss is not quadratic, then the third order term is going to matter. So this is the main thing I want to kind of like convey today, but unfortunately, just because this is complicated, so I probably wouldn't be able to do everything rigorously. So I just really can't do everything rigorously. So what happens is that if the loss is not quadratic, then recall that what happens is that you have xt plus 1 is equals to 1 minus eta h xt minus eta ct minus eta t xt plus higher order term. And this is happening. So this is working in K, because I assume that H is working in K and the noise is always in K in the subspace. So this main part is always working in K. You are bouncing around in K. And this is working in K perp. And that makes them kind of completely separate. So there's nothing you can control the third order term. The third order term can build up for a very long time. So so maybe this is let me see. So basically, let's see. So I probably will go to this figure multiple times. Right, so this is what's happening here. So I don't think I can draw anything here. So, but maybe first watch it, and then I'm going to go to a static figure so that you can I can annotate. So this is the stochastic within set on this in this valley. And you can see that it's moving in this valley. So now let's look at a static figure. I think I have one somewhere. So in our language, the mathematical language, so this direction. Okay, let's see a different color. So this is the direction of the K perp, and this is the direction of K. So this direction is K. Okay. And so, but here, this is not a quadratic because at least it is not a quadratic because at least the k-perp direction does matter to some extent. Because the k-perp, you can see that if you go from here to here, you're going to go to flatter and flatter region, right? So what happens is that most of your work is in the k direction. You are just bouncing around in k direction. But there is some third order term that drives you in the k-perp direction, and that can build up eventually for a long time, right? Recall that you start from here, you do a lot of like bouncing around, but eventually after you bounce for so long time, you move in the k-perp direction. And this is just because the third order term is accumulating for a long time until you go to the flatter region. So the main term is doing the bouncing, and the lower term is accumulating in the direction of the valley. Any questions so far? I can go. I'll go back to this figure probably once again, just once I do a little bit more math.
If we sort of know that this is happening, like what we want to do is first like run really far just in the k-perp direction, and then like, is that a feasible thing we can do?
Yeah, that's a great question. So if you know this is what's happening, why not just do something more explicit to make it faster, right? So I think there are several. Let me see. So there are several things that like this is a good question, but this is not something super new. Like people have thought about it, and I have thought about it, and I think there are multiple constraints we have to kind of respect. Like I still think this is a feasible direction to go, but it's not easy. So and I don't think there's an existing paper that can really achieve this very well. So one of the things is that, so how do you go to the valley? So what you want to do? You want to go to the valley. You want to compute the direction of k-perp and you go there, right? So how do you go to the valley? I think that's not too hard because you have to use, but not trivial, because to go to the valley you have to either decay your learning rate or make your batch size bigger so that you have smaller noise. But that requires paying more compute because you want to be more accurate, so that you. Right? Sometimes you want to be more accurate in the k direction, right? So it requires more compute. So that's one small thing, right? So whether you really can afford those compute to really go to the valley in the first place, I think you can probably. In most cases you can, but it's not like for free. So you do have to consider the cost. So and then you go to the valley and then you do this, right? You move in the k-perp direction. But the problem becomes that the real picture is not just one single. It's actually, this is only a local view. So once you go to here, maybe, if locally it sounds great, I'm going to a better place. But maybe there's actually, this function has a lot of other parts. So actually you have to travel really far, very far away somewhere else. So then you have to do this again, this local view again, and then try to do it, and so on and so forth. Right, so then it becomes, then you have to also find a new valley, and then probably find the direction of the k-perp. And also finding the direction of k-perp is also not that trivial because it requires computing the third order derivative. Computing the third order derivative on one example is still okay. It costs you, computing any order derivative on one example takes you a constant factor more than computing the first order derivative. This is a very interesting thing about deep learning. So computing any derivative requires almost the same time as computing the first derivative, as long as your output is a vector. So, but you do have to pay a constant factor, something like 2 or 3 times more on compute, and also you have to do this for and this k-perp direction to get it exactly. You also have to do a full batch, full epoch, because so the third order term is the third order derivative of the full function of the population of the population function of the full empirical function. So if you use a mini batch thing, then maybe you wouldn't get the k-perp direction very accurately. So there's a bunch of decisions which make it complicated. We don't even know exactly which one is the bottleneck. So it's a little bit tricky. So. But that's a great question. Yeah. So we tried very hard to somehow do this for quite a while already. Yeah. So Okay, all right. So now let's see. So I think I'll do a little more math just to kind of give you a small feeling about how do we proceed to analyze this. So, and the way to analyze this is that you somehow view this as I said, as a two things. So you first define a companion process, which is easier. So define ut plus 1 to be 1 minus eta h ut minus eta per ct. And this is well understood, because this is space where you are doing optimization on the quadratic approximation. And we have done this already. So, and then you characterize the difference between them. So xt minus ut. We define this to be rt. So basically the main question is that what rt is doing. And we can we can compute the recursion of rt. Right, this is equals to, you plug in the definition of xt plus 1 and ut plus 1, you get 1 minus eta h xt minus ut minus eta t xt plus higher order term. And then this is 1 minus eta h rt minus eta t xt. And the interesting thing here is that you still have the contraction. And this is the bias or the regularization effect, but there's no noise anymore. There's no stochasticity. No stochasticity. You know, there's still a little bit of stochasticity in xt, but at least you don't have the ct term that you have added intentionally. Just because you are taking a diff with the stochastic trajectory. So, and you can actually remove the xt as well, because you can basically claim that this is close to the version where you plug in, you don't plug in xt, you plug in ut. This is just because xt and ut are somewhat similar. Of course, you want to understand the exact difference, but for this level, especially because you are multiplying eta here, so like the further differences becomes even higher the term you can drop. So, and now what happens is that if you look at the diff, if you look at in the subspace of K, right, which is the span of H, this is still a contraction. Because you have some additional biases, but the biases will be corrected by the contraction eventually. So, however, for the inner K-perp subspace, the contraction is gone. You project everything to the K-perp subspace. Then you get right. So the H doesn't have any effect anymore, because H has nothing to do with the K-perp direction. You just project it out. So now the thing is really simple. So in the K-perp subspace, you are just basically taking the previous RT projected in the K-perp subspace plus something new. So basically, you are just adding up things. You don't have any contraction even. So if you do this, recursively, you are going to get the K-perp of R0 minus the sum of and now it becomes, the question becomes, how do you understand the sum of this third order term? And by the way, I've never told you where the third order term is going. Right? I only claim that there is a third order term. I didn't really say where it's going. So now the question is what the third order terms are going in average, right? So in the long run over time. So we can kind of ignore this. This is just a restriction to the subspace. So if you look at the the sum of where the third order term is going. So this you can so first of all, let's assume maybe this is a organal heuristic. Let's assume UT. Let's say S is something like UK transpose. This is the covariance of UK. This is as k goes to infinity, and also assume this UK mixes as a Markov chain. I'm not sure whether you are familiar with this Markov chain mixing, but you just assume that UK is kind of like doing the bouncing, right? UK is doing the bouncing around. You assume that it's really just doing that. It's kind of like a Gaussian. Then, and S is the covariance of the Gaussian. And then this one, you can rewrite this as, you know, T of, in some sense, this is like equals to little t times, roughly equals to little t times the T with the expectation of U, UK transpose, or maybe with S. So I guess maybe, so what I'm doing here is that suppose you have some variable U that is drawn from S, from Gaussian with covariance S, then the expectation of T UU is equals to T of, this is expectation, I guess let's look at the ith coordinate, then this is sum of J Tij k uj uk, and you look at the ith coordinate, the ith, okay, to this, and then you switch the sum with the expectation, you have jk Tij expectation uj uk, and this is sum over jk Tij expectation UU transpose. You take the JK coordinate, and this is, you know, you denote this by T of expectation UU transpose. So you can also apply the tensor on a matrix, and the definition is really just this. So the definition of T applied on a matrix is that you have some of Tij nice JK. Anyway, so I think this might be a little bit too much for this course, but anyway, you can basically, at the end of the day, what you have is that you build, I guess there's an eta here, my bad. So this T comes from, you have multiple times, right? You have T steps. That's why you got T. And eta is what you got from this eta. And this is something like you apply the tensor to the average covariance, the mixed covariance thing. So basically the question becomes like, what is S? If you know S, then you know which direction you're going. And you know how far you're going. You are going by T times this direction because you take T steps. So the final question is that what this TS is. And this is very informal and not even exactly correct. And to fix it, you need something a little bit more derivations. So this bias direction T of S, right, minus T of S is the bias direction. So this bias direction is equals to minus, I guess remember what's the T? T is the third order derivative, and S is the iterate of the, you know, S is just a matrix for the moment. And you can rewrite this. So if you think about what is this? This is the gradient of the inner product of the Hessian times S. So, right, this is the equation. And in some sense, you can argue that this is a heuristic argument, and actually it's not even a correct, not even 100% correct argument. So the TS is trying to make nabla squared gx times S smaller, because you are moving in the gradient of that function, right? So let's define this to be Rx. Right, so you are moving in a negative Rx, negative nabla Rx direction. That's why you can argue that you are trying to make that function smaller. So the additional bias is trying to make this minus TS term is trying to make the Rx smaller by moving in the gradient of this Rx direction. So, and eventually, I think if you work out all of this kind of like subtle details, right? So with a lot of other like steps and fixes and assumptions, you know. And I think I'm not going to go through all of this. We're already kind of running late. But you can somewhat prove in certain cases. Let me just write down what finally you can prove. So can prove something like SGD with the so-called label noise. I didn't tell you what label noise means. It doesn't matter. It's the one kind of noise. It's not exact. It's some additional noise, and converges to a stationary point of the regularized loss L plus lambda R, L hat plus lambda R, where R theta is roughly equals to trace of the Hessian of the loss. So yeah, so I guess there's no need to understand any details here. In this, there are some other subtleties, there are other assumptions, so on and so forth. I just want to give you a taste on what kind of theorems you may hope to prove. So basically you are saying that if you run SGD, okay, this is on the original loss on L hat. So if you run certain kind of SGD on the unregularized loss, it will convert this to the stationary point of a regularized loss. So that's why you get this regularizer for free. And what regularizer it is, here the regularizer is the trace of the Hessian, is something about the flatness of the loss L hat, right? The Hessian is the curvature, the trace of the Hessian is about the flatness at that point. So you are implicitly encouraging the flatness of the loss function. So, but this has a lot of things hidden here, and actually I think I'm missing a few kind of important assumptions. You know, I'm not writing down some of the important assumptions just because they are not, you know, it takes too much time to write down. But this is kind of like something we may hope to prove under certain cases. Okay, any questions?
So it seems like the following your derivation seems like it will also have a regularized and some high order derivative as well. Since if this goes to zero, then it won't have to buy the high order.
That's a great point. So the question, just to rephrase the question, is that whether the even high order derivative, the fourth order gradient, would induce a bounce. I think on the conceptual level, if your third order thing is not zero, then I think the fourth order one wouldn't matter that much. And if the third order term is zero, I think indeed there should be a fourth order. The fourth order term would have effect. Yeah. But so far we're not thinking about we are assuming the third order term is doing something non-trivial. So that the fourth order term will be dominated by the third order term.
I think this is like one sort of order change. So you want yourself to stay in the point where
in the last theorem, the stationary point is. Okay,
so the regularization is on the trace of the Hessian, right, instead of the third order.
Oh, I see. Yeah. So the question is why the regularization is the trace of the Hessian. This is because when the regularizer is about the second order term, the second derivative, then the direction you want to move to is the gradient of the regularizer. Right? Because so when you have a regularizer, what do you really mean? It means that you should move to the direction of the gradient of the regularizer. That's why that's how they match up. So actually the direction you really move to is the third order derivative, depends on the third order derivative of the loss function.
And then the second, so the Hessian becomes effectively zero. That's the U would be dominant and kind of circle. And then the first order term would one from the other, you kind of choose the circle term to zero.
So I guess there are two views. One view is that you look at it on the regularizer level, then it's currently it's the second order term, the second order derivative of the loss. And another view is that you look at the actual the iterate space. Then currently is the third order derivative. It's about third order derivative of the loss. And suppose in the iterate space, the third order derivative vanishes. Then you have to talk about the fourth order derivative of the loss. And in that case, the regularizer probably will be about the third order derivative of the loss. Just because your regularizer is always one order up compared to the direction you want to move to. Does it make some sense?
Another related question is, so the FGD prefers this flat space, flat stationary point. So what's special about what are the special properties of this kind of flat stationary point in terms of the general validation?
Yeah. So why flat stationary point is better? Right. So I think yeah, whether it's better or not. So I think I'm going to talk about that immediately in the beginning of the next section. Yeah, the answer is that we do believe is generally better. It depends on some. It kind of relates to the Lipschitzness of the model. So I'll discuss more next week. No, Wednesday. Thanks. Bye.